Hello and welcome to my presentation about Zermelo-Fraenkel set theory. Today, Zermelo-Fraenkel set theory is the most popular axiomatic set theory system, and it can basically be used as a foundation for all more complex mathematical structures. First, we'll have to talk about the first set theory ever developed by Cantor, the so-called naive set theory. Then after that, we talk a little bit about why it was flawed by looking at the Russell paradox. And last but not least, we'll take a look at the axioms themselves. The naive set theory did not provide a system of axioms, but a simple definition of sets, which goes as follows. A set is a gathering together into a whole of definite distinct objects of our perception or of our thought, which are called elements of the set. With this definition, we can take basically any objects and put them into a set. For example, S is the set of all objects for which P is true. As already mentioned, this theory was invented by Georg Cantor in the late 19th century when he was trying to make theories about infinity. The problem is that his definition is very simple and too broad and therefore leads to paradoxes. The most famous one being the Russell paradox, which can be observed by looking at the set of all sets which do not include themselves. The first question one has to ask is, can a set even be an element of itself? If we look at our naive definition, the answer is yes, there's no reason why this should not be possible. The paradox can now be found by asking the question, is R an element of itself? Because if it is, then it can by definition not be an element of R, and if it's not, then it must be an element of R, which means that the statement that R is an element of R is true if and only if its negation is also true, which is of course logically impossible. There are more paradoxes which are all more or less similar in the way that they observe some kind of weird counterintuitive set. To overcome those paradoxes we need the Zermelo-Fraenkel axioms. The first one being the axiom of extensionality, formally stated like this. It basically says that a set is uniquely defined by its elements, which also means that any kind of order inside the set is completely irrelevant. The next one is the axiom of specialization, which is not a single axiom but a scheme which can produce an infinite number of axioms. It gives us the possibility to define a set Y as a subset of already pre-existing set A, which would look like this. This is set A, and now we can take the subset of it. This axiom is particularly important because we can now prevent the Russell paradox with it. If we try to construct the set R with this axiom, it would look something like this. Not only must X not be an element of itself, now X must also be an element of a predefined set A. This can be formally stated like this. If we substitute X with R and negate the statement, then we arrive at this. If we now try to keep the statement true, we must accept that either R does include itself or R is not an element of A. And since we know that the statement that R includes itself leads to the paradox, we can rule that out. But since it is a necessary condition that R is an element of A, R cannot be constructed with our axioms so far, and is therefore excluded from the set theory system. There is another axiom which is capable to prevent the paradox. It is the axiom of foundation. It states that every set needs to have a smallest element. That excludes every counterintuitive set that is an infinite sequence or any kind of circular sequence of sets which do contain themselves. Of course, the set R by Russell falls also under that definition and is therefore not only not derivable from the axioms, but also strictly forbidden. There are of course a lot more axioms, like for example an axiom which postulates the existence of the empty set, an axiom which allows us to pair two sets together into a new one, another axiom which lays the foundation for the union of sets, another one which allows for the existence of the power set, an axiom which postulates the existence of infinite sets, and an axiom that states that the image of a set is also a set. The last axiom, the axiom of choice, states that there exists a set which contains just one undefined element for each set of a predefined system of sets. It is very controversial and its validity is even today still disputed. Furthermore, it is important to mention that some of these axioms can be derived from each other, especially regarding the axiom of replacement, but for a better presentability, they are usually still included in modern portrayals. That was my presentation about Zermelo-Fraenkel set theory. I hope you enjoyed it. Thank you very much.